Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz. I'm glad you've taken the time to join us today as we look at our topic of the 5 key error prevention techniques for the assembly process. Now, when we talk about error prevention or error proofing, Shigeo Shenjo says that defects occur when mistakes are allowed to reach the customer. And so this is a big mantra of the error proofing philosophy, that if we can take care of mistakes before they happen, or if we have the opportunity to correct them when they do happen, then we can move to a zero defect type of assembly, or at least error proofing scenario. And so you may hear the term poka-yoke or poka-yoke. These are all terms that deal with the Japanese philosophy of error proofing in relationship to the assembly process. Now, we do have error proofing concepts that we see throughout our daily lives. And those things can be like if we're going to start our car, we need to have the car in park and our foot on the brake for that to go ahead and start. If we're going to be going into an elevator, there are sensors on the door to prevent someone from getting caught in those doors. We also see these in scenarios where we're getting gas, so the nozzle will automatically shut off when the tank becomes full. Or if we're plugging something in this case, we're plugging in a charger to charge a vehicle. And this charger will only fit into the receptacle in one direction. So we can't make a mistake. So we're basically allowing our behavior to not make a mistake. And this is the concept behind the error proofing principles. And when we see that in relation to manufacturing risks, there are certainly, if you've been with us or seen any of our webinars, we do talk about these risks that we typically see in the manufacturing process. And when it comes to defects and errors, we're producing either scrap when this happens or rework. And in both cases, this is an expensive thing to deal with. And so if we have the opportunity to be able to create or craft behavior in a way that the operator or the assembler can't make a mistake, then that puts us on the error proofing path. And so when we look at the human risk within the assembly process, this is where a lot of the issues can present themselves, especially when we're dealing with rework or scrap, because people make mistakes. They don't pay attention. They forget, or they miss a part, or in our case, or miss a fastening. And so the human element plays a vital role in the assembly process. Now, if we can again move the operator to a direction of where they can't make a mistake, then we are trying to basically reduce all of those inputs as it relates to the human element. But what are some of the defects that can be caused by that element? And when it comes to torque and the fastening process, obviously we talk a lot about either under torquing a fastener or over torquing a fastener. Fasteners that don't get fully torqued, you may have a lifted type of head, or the fastener may be skipped altogether. And so these types of defects will present themselves later on if parts become loose and fail because of the improper tightening procedures. And again, if it's over torqued, then any type of shock or vibration can cause that fastener to break. If it's under torqued, again, shock or vibration will cause the fastener to completely fail as well. And so if we can ensure that we're getting the correct torque that we need with the correct clamp load, and that the operator is doing everything that we would like them to do, then we can help to minimize the types of error rates that we might see with a particular operation. So when we talk about error proofing and some of the principles, a lot of this may seem a little bit elementary, but if you take a look at the overall concept of these principles, then it may be able to help you look at what you're doing with your particular applications and find some good use of these principles there. And so the first principle is eliminating the possibility for there to be an error. And by doing this, this is obviously preventing less errors to happen. With the actual parts that we may be using, you may be looking at replacing some items with a newer technology that may be able to help in that particular area with perhaps automation equipment, or looking at how we can automate a certain process throughout the step. And that automation doesn't necessarily mean a physical replacement to either a robot or a cobot, but we're talking about things within the actual process that can help us to automate that. That could be either the use of input devices or barcode scanners, things like that that can help to move the process and help detect any type of error that may be happening. Again, to help minimize the amount of errors that we may see within the actual process of the assembly. Now, we've looking at the 5 key error-proofing fastening techniques. And so we're going to roll through these with basically with the idea of our demonstration that we'll be giving, and that's going to be with the use of our new MD Mini DC low torque control tool. But these concepts can be used with other brands of DC tools, or they also could be used in the use of standard electric clutch tools, or even hand tools in some scenarios. But for the first key in our error-proofing fastening techniques is obviously we want to ensure that we're getting the proper torque control within the assembly. Now, again, this can be done with a DC tool like we'll be showing, but it also can be done with the use of a torque analyzer and a torque sensor. We can use an inline sensor to help measure what is happening with the assembly. So we're measuring the tool actually on the part, and we can ensure that the torque control that we're getting there is correct. We do have other webinars that deal primarily with this type of testing and auditing process, but we want to ensure that the torque control is correct. And so with the different tools that we have, you have that ability to do that. Next is going to be process control. So with our second key here, how can we do our assembly process within its assembly as a particular job, or as an entire build process? Can we put that in with our assembly that we're looking for? And that would be, again, with the use of automation devices. They can be, again, barcode scanners that can change certain parameters within the actual assembly. They can change a preset on a specific tool that we may be using. It can help run through a particular assembly. and with in and output controls. So managing the entire process of the assembly, if we have that ability where the operator doesn't have to go and change a preset on a tool, doesn't have to grab a different tool. But if we can manage that process, then we can, again, help to create a smooth and error-free process. Next is going to be screw counting. Now within the managing of our process controls, there is an element that we do have that we can use a screw counting feature within the assembly. But if you are using a clutch screwdriver, there are other devices that you can use. We have our Scout screw counting system that allows you to ensure that you are getting the correct number of fasteners for a given assembly. And this can be done, again, on the DC side, can be done with the electric clutch tool. It does make this difficult if we are using a hand tool scenario where you may be using a torque limiting screwdriver. So that may be a situation where you may want to move from a manual tool into the use of an automatic tool if you are doing or concerned about fasteners that aren't being counted or aren't being correctly done within the assembly. So screw counting is a big component that we can leverage in making sure that all of our fasteners get done and get done correctly. The next item is going to be job management. In our ability to create different process control jobs and scenarios, do we have the ability to manage those particular jobs within the assembly process? So if you have a low volume, high mix type of scenario, do you have the ability to manage those jobs either through an input device, a PLC, or within the tool itself? But if you have that ability where the operator brings an assembly into the cell, scans a barcode, it automatically sets up everything for that particular job, then that would be ideal in being able to make it easier for the operator. Because again, what we're trying to accomplish is making it easy for the operator not to make a mistake. And that can be done through the use of different input devices through a job management program. And that can also be facilitated through an MES system or something like that. So if you do have that type of system, then it would make sense to be able to introduce or include tools that can communicate with that MES system to allow that to be able to function together and produce the actual correct assembly process for the operator. And lastly, we have a real-time monitoring. And so this kind of goes back to the sense of using the system with a torque analyzer and an inline rotary sensor where you're getting real-time information. Now you may not be able to have that for every single rundown, but if you do have a DC type of tool system, then you do have that capability to monitor all of the data that comes from the tool. That data can be analyzed and reviewed later, and you can see where there may be needs in being able to change a parameter, looking at changing the actual process, but that does allow you to look at being able to take a step back, grab the data, and see where you might be able to make improvements there. With the real-time monitoring, it also gives us the ability to catch a mistake or an error that may happen right away, giving the operator the chance to go ahead and fix that right at the time. Again, not allowing that part to move forward throughout the assembly and cause a defect or an error down the road. And so that is the basic 5 keys to our fastening techniques as it relates to fastening. And so if we jump into our poll question for today, we can go ahead and launch that. And we're asking today a pretty simple question. It's either a yes, no, but are you currently using any error proofing tools in your assembly process at the moment? So we'll give you a chance to go ahead and answer that. And I will grab a drink of water. All right. Thanks very much for participating here in this poll. It looks like we're about at 40% or so with error proofing assembly, and then 60% no. And so that is gives us some opportunity to look at our tool or demo and looking at how this can relate to a specific tool and assembly setup on how we can do our error proofing process. And so we have, like I said, our MD Mini low torque DC tool. And so this here is our display. It is not very big at all. And then we also have a thread block here with some M2 fasteners. And we are dealing in our inch-ounce range on our controller currently right now. And so what you see here on the screen basically is we have our preset here. We have what our target torque value is, our RPM speed, we have our count function, and information regarding the last rundown. But with our error proofing processes, let's take a look at how we can use some of those principles in setting up this particular tool for a fastening process. And so the first thing is we want to ensure our torque control. And we're going to want to first set up our preset torque. And in this case, I can enter into our program menu, tap on our menu, I enter in our password. And this brings us into our main menu. Whenever we do changes for the preset, that's going to be done in our parameter mode and in our fastening tab. And so down on the bottom here, you'll see that we are using, right now we're in preset 1 of 15. If I wanted to change to a different preset, I can just simply tap in this area, select which preset we want to work with, and we can do that there. But we want to go ahead and ensure our target torque. And so to do that, we can come in and we can just simply select our torque value that we need. And if we want this to be set to 4.25 inch ounces, we can go ahead and enter that here. And so now we have that torque value set. The next thing that we're going to want to do is program our tolerance. And so if we get a value that is going to be outside of our target torque, then we will get an error alerting the operator to reattempt that fastening. And that's done right here on the same page. We have our torque limit percent. Currently that's set by default at 10%, but we can modify that if we want. We could change it to whatever percentage that you might need for your particular application. But we'll go ahead and we'll leave it at 10% here for that for this operation. And so now if we want to go ahead and we want to run our fastener down, again, we're dealing with preset 1. So I can come back out and we're on preset 1. We have our target torque at 4.25 inch ounces. And I'll go ahead and run this down. Okay, so we got our torque value and everything was within those limits. And so that was would be considered a good fastening rundown. So now if we wanted to send this to another level of error proofing, what we would do is now go ahead and program our angle tolerances. And so what this allows us to do is to be able to check for errors that may be considered either a stripped fastener or possibly a cross-threaded fastener. And so we would come back into our menu. And we have the ability to set our angle limits here. So on our second page, we have our min angle and our max angle. And so with these fasteners here, we have them currently right now at about 3,000 degrees of rotation before they seat. And if we were to have a cross thread type of issue, that's going to happen right at the very beginning of the rundown where those threads are going to catch and bind, and then the torque will be met. So that will happen pretty much right away. But if the operator is not paying attention, the tool hits torque, they just go ahead and move on. So with that, we can go ahead and set our minimum angle. So let's say that our minimum angle needs to be at least 1,500 degrees. Excuse me. 1,500 degrees of rotation. We can also set our max angle and say that is 4,000 degrees of rotation. So now we've added another layer of error proofing on the fastener here. So if we come back out on preset 1 and we want to go ahead and run this fastener down. Okay. So we met our torque value at our target torque of 4.25 inch ounces. We also hit our angle correctly. But what if we did run into that cross thread event? So I have this fastener pretty much to simulate the cross thread. And so we got an error where it said that we did not meet the minimum amount of turn. So then the operator would have to come back and try that again. And if we are over the angle, this would simulate a stripped fastener. Or if we go to a scenario where if I just turn the tool on, let it run, and the fastener stripped, we would get the angle over error. So again, we've added one layer of error proofing with the torque, with our tolerance, and also with the angle requirements that needed to be met. The last thing that we can do here is we can enter in a fasten stop alert. And what this does is it will add one more layer to our error proofing, where because we're monitoring for angle, with this particular fastener, we're monitoring our angle from when the tool starts. We want to make sure that the operator runs the tool down until the operation is complete. And so for us to do that, we can enable our fasten stop error. And this is on page 4 of our controller menu. We'll turn that on. Now, if we come out and we run the tool, but if I let go of the trigger before the operation is complete, we will get a no torque complete signal, an error. And so in this case, the operator gets an error, they did not let the tool run all the way down and finish its assembly. And so that would be the scenario of where we're wanting to ensure our torque control, again, with our target torque, our target tolerance, our angle windows, and then finally the fasten stop error there. So in our next process here is going to be the ability to add process control to this assembly. And again, the process control can be implemented by the use of an input device, communications with a PLC or an MES system to go ahead and provide the controller with the correct presets to use within the assembly. But we do have a mode in here that allows us to be able to set up the assembly right in the tool. And this is going to be our model mode. And so a model is basically like a job where we have 20 different steps that we can use within this job. And we can call out different things to happen at different times throughout the assembly. So in this case, let's just say we have a 5 fastener assembly. We'll use these 5 here. But these first 2 are a preset 1. This one down here is a preset 2, and these final 2 are a preset 3. We can have all of that set up here within the model function. So we can come in, we can select which process we want to run. So this is going to be a fastening. We can tell it which preset we want to use. So it would be preset 1, and that is for a count of 2. And then our next step will be a fastening. We'll do preset 2 for a count of 1. Our third will be, again, a fastening on preset 3 for a count of 2. And so what will happen is once we select this particular model, each model can be made up of the 15 different presets that we have available. So if we come back to our controller menu, we basically need to tell the unit, do we want to run in the preset mode like we were, or do we want to run in the model mode? So in our controller menu here, we can go to our model selection. We turn this on, and then this will put us into our model mode. And so the screen up here looks a little different. It is in our model. And what this is showing us is that we are using model 1. It's preset number 1, and this is our first step, which is a fastening step. And after we get a good signal for our rundowns, then we will index through the assembly. So we can run this fastener down. We get a good signal. It counts it. You can see that our count right here went from 2 of 2 to 2 of 1. And when we run this one down, it now changes our count to 1 of 1. And now we're on preset 2, our step 2 of our fastening. I accidentally hit the button there. And now we can run this one down at our other preset value. And now we have changed to preset 3 and step 3, and we can run these final 2 down. And now our model is complete. So now at this point, we can either have that model restart, or we can have a barcode scan, or again, a communication from an input device automatically select which model needs to be done based off of whatever part may be coming into the assembly. And so with this, we get the ability to select the correct preset that needs to be done. And then we also have the count function that allows us to be able to know where we are within that particular account. And then the last would be the programming of multiple presets, which we just did. And then we have our real-time monitoring, which gives us all of this information here that is either stored locally on the controller, or it can be streamed out to another collection device, sent to an MES system, or to another collection for that. But this will give us all of the data, the time date stamp for the operation, what the torque was, what the preset torque was, how much angle did it take, what was the RPM speed, the amount of time in milliseconds it took to run that down, if there was an error, what that error code is. So all of that information can then be used to look back at the assembly and see where that particular operation may be able to be improved with that. And so with that is going to move us to our questions and answer section for today. Today, Ashley will be reading the questions. So Ashley, do we have any questions?
Morning, Dave. The first question is, what is the difference between a transducerized and non-transducerized tool?
So the main difference is that a transducerized tool basically has a measuring device or measuring sensor built into it. So it is measuring the actual torque that's being applied. The other type of a DC tool would be a current based system, where it matches the torque output based off of the current draw within the system use for that particular tool. So that is primarily the difference. One has a measuring device in it and the other one does not.
Okay, another question we have, the tool is getting stuck in the hex of the fastener. Is there a way to turn the other way a few degrees so they do not get stuck?
There is, and within the programming of the tool itself, you can use what would be considered the angle after torque up. So that would be where we can come into our advanced menu for a particular preset. So again, we're using preset 1. We can go to our angle after torque up window. We can set a speed, say 100 RPM, and we want to turn 5 degrees in the reverse rotation. And so now when we were to run that, it will back that off in that increment. Or you could do some testing to see if that, if you need what angle works best without changing the actual clamp load of the joint, but that is possible to do with the angle after torque up.
Okay, another question we have, is it possible to get the raw data?
Correct. Yeah. The data from the tool itself can either be stored locally on the controller or it can be sent streamed out of the controller as well.
Alrighty. Another question, how many workflow or fastening sequences can be programmed and stored with the system?
So we can have with the 15 different presets that we have, you can have up to 15 different models with 20 steps each. Each step can have up to 99 fastenings. So based off of your need, that is where we're at. We are expanding our DC control line from 15 to 31 presets here very shortly. And that will then extend the amount of available programs to be used at that point.
Okay, and then another question, can this system be programmed and used for thread tapping applications?
It can. We can set instead of looking for a specific torque value, we can set an angle amount to turn the fastener, or if you want to turn a tap, you can do that to run to a certain amount of degrees of rotation, and we can put a threshold of a max and min torque. So instead of a torque control where we're looking at a min and max angle, it would be angle control where we have the ability to monitor the torque. So if we are turning a tap and it goes above a certain torque value, we can get an error, or it can run through run to its degree of angle without error. Then it will go ahead and finish the process.
Okay, and then someone's wondering, how can the collected data be presented in a spreadsheet, chart, etc.?
Yeah, the data comes out. If you're going to dump it into a spreadsheet, then it's all CSV, and depending on how you want the data to come, you can parse it however you might need it.
Okay, and then we have, can you tie the raw data to a lot number or serial number?
Yes, that is possible. So if we scan a barcode, so one of the data fields is a barcode, and you can scan a barcode. It dumps that barcode into the data stream. So every value that is done after that will be associated to that barcode, and that will remain until another barcode is scanned or the system gets powered off. But in that case, you can add that barcode to the data.
Okay, and then it looks like we have a question that says, do you have a EEG of raw data? Might not be able to answer that one.
Yeah, I'm not quite sure what we're looking for there.
Okay, then we have, do you have a tool bit identifier if a model uses different bits?
Identifier if the tool use different bits. Yes, each tool can have its own basic ID number that can be used. So that is possible. We also do have bit selectors, or excuse me, a bit socket tray that can be used to, again, make sure that the operator is using the correct bit for a particular operation. So that is where it will tell the operator which bit to pull. The operator pulls that bit, replaces the bit that was in the tool, and then the tool will be allowed to work. So the bit socket trays can help with that as well. But yes, each tool does have its own unique ID number.
Okay, and then do we have an example of data that we could show?
I don't have one here, but we may, it would be in one of our manuals for our DC tools.
All right, that looks like the end of the questions.
Awesome. All right. Thank you very much for joining us today. And we look forward to seeing you next month, or if you'll be headed to the assembly show in Nashville at the end of the month. So with that, thanks very much, and we'll see you next time.